Okay, dear student, uh, the temperature at P point is theta and Q point is theta plus d theta by dx del x. D theta by dx del x, this is the change of temperature uh, from P point to Q point. Suppose if for each dx distance, the change of temperature is d theta. Then for unit distance, d theta by dx, and for del x distance, d theta by dx del x. And at P point, the temperature is theta, and at Q point, the temperature will be this temperature theta plus the change of temperature from P point to Q point. Okay. uh, Now what is the amount of Q1? Q1 is the amount of heat energy that enters the PQ section. What will be the uh, Q1? Q1, the what will be the equation for Q1? Q1 Ka theta 1 minus theta 2 divided by x. And we may write this equation as Ka d theta by dx, just theta 1 minus theta 2 by x, and there is one t kat theta 1 minus theta 2 divided by x. We may write theta 1 minus theta 2 as a d theta, and x we may write x as a dx. For 1 second, that means the rate of flow for Q1, if we consider Q1 as the rate of flow that enters the PQ section, then T will be 1. Then we can write Ka d theta by dx. And d theta by dx, temperature gradient, d theta by dx, theta 1 minus theta 2 by x, this is the temperature gradient. We may write this temperature gradient as d theta by dx. This is the fall of temperature. Then we may put minus sign, because for fall of temperature, decreasing of temperature, minus. Okay. Then d theta by dx, okay, minus Ka d theta by dx. Then you see Q1 minus Ka d theta by dx. Theta is the temperature of at P point. At P point, the temperature is theta. Now Q2 minus Ka d by dx, and here the theta, this theta is for Q1 at P point, and now there is what is the temperature of Q2 at point Q. At point Q, the temperature we found theta plus d theta by dx del x. D theta by dx, this is temperature gradient, and this is also the temperature gradient. And this theta theta is the temperature at P point, and this is the temperature at Q point. Now, what will be the gain of temperature, gain of heat of the PQ section. This layer will gain amount of heat energy. How can we write this heat energy? Simply Q1 minus Q2. Q1 minus Q2. This is the gain of heat energy of the layer PQ section. Therefore, Q1 minus Q2, that is this one minus this one. So this one minus this one minus this one, minus plus. Now just simplifying, just cut where it may be cut. Simplifying this equation, you may write this will be Q1 minus Q2, this one, and equal to, and by simplifying you may write, you will get Ka d square theta by d x square del x. Really, Q1 minus Q2 equal to Ka d square theta dx square del x. This is the gain of heat energy. This is the gain of heat energy of the section PQ. Now, this amount of gain of heat energy, actually there are two parts. One is finally absorbed by the layer, and other part will be radiated by the layer or PQ section. This amount of heat energy, we may split up this amount of heat energy. One part is absorbed by the PQ section or layer, and the other part will be radiated by the PQ section or by the layer. Then the absorbed heat energy, absorbed heat energy equal to mass into a specific heat, into temperature change or rate of rise in temperature, rise in temperature. Mass means volume into density, then a specific heat, and the rate of rising temperature. The rate of rising temperature means d theta by dt. Volume into density into a specific heat into d theta by dt. D theta by dt means rate of rise in temperature, rate of change in temperature. So volume volume means volume equal to area into distance, then density, then a specific heat, and rate of change of temperature, rate of rise in temperature, d theta by dt. This is the absorbed heat energy, the equation for absorbed heat energy. Now the radiated heat energy. Radiated heat energy equal to emissive power into surface area and the temperature. Access over the surroundings, temperature, average access temperature of the environment or surroundings. P and del X, this is the area. Area means two dimension. One is P and others is del X. 2. Here P means perimeter, porishima. Perimeter, this is one kind of length, and del X is the width. And P is perimeter or porishima, this is length, and del X means width. P into del X, this is area. E is the emissive power. Emissive power means the quantity of heat radiated from the surface per second per unit area per unit temperature difference. So this is the radiated heat. This is the equation for radiated heat energy. So this gain of heat energy, actually there are two parts. One is absorbed heat energy and others is radiated heat energy. So this one equal to this one plus this one. This one equal to the gain of heat energy equal to A del X rho S d theta by dt plus E P del X theta. The gain of heat energy equal to absorbed heat energy plus radiated heat energy. Now simplifying this equation, you may get d square theta by dx square equal to rho s k d theta by dt plus E P K A theta. Similarly, transferring these terms to the left side, you may also get d theta by dt equal to k rho s d square theta by dx square minus p rho sa theta. D theta by dt equal to k by rho s d square theta by dx square minus P rho as a theta. E means emissive power and P is the perimeter. Finally, you may write this is the required equation. This is the required equation. Or k by rho s, these are the constant. You may write k by rho s as h. K by rho s as h constant. Similarly, P rho as a you may write this one as a mu constant. Okay. Finally, this is the required equation. This is the standard Fourier equation for one-dimensional flow. One-dimensional flow of heat in the variable state. One-dimensional means a long bar. The heat flows along a bar. This is one-dimensional, and variables means different temperature. Through this bar, you will have different temperature. This is a variable state. Okay, student, you try this video class, and also you slide presentation. This will help you to understand physics, and next I will send you next classes. Thank you.